When Apple first came out with facial recognition, it was the new cool thing that everyone was excited about, replacing the low tech, obsolete Touch ID. Yet nowadays, we take this amazing feature for granted. But how exactly does it all work? Well, it's done through an algorithm known as convolutional neural networks, or CNN for short. There are two main parts to a CNN: the feature extraction part that involves convolutional layers, and the classification part that uses a simple neural network. We will be focusing heavily on the math behind the feature extraction portion. So all you need to know about how the classification part works is that you pass in a 1D tensor, which is simply an array that can be ran on a GPU as input into a neural network. This will return a certain number of outputs that are known as classes, which label what an image is. This is the CFAR10 dataset, commonly used to train CNNs on. As you can see, there are 10 labels or classes that the models can output, ranging from airplane to bird to ship. These classes are what the neural network will output, as I previously mentioned. Now, how does feature learning work? To give a broad overview before we dive into the specifics, there are 6 main steps. We start with a convolution layer that extracts features from an image through filters called kernels, which will result in a feature or activation map. This map is then normalized using a function called ReLU activation. A pooling layer is then applied onto this activation map in order to reduce its dimensions and provide computational efficiency. We can then repeat this process as many times as needed to increase the complexity of the feature maps we create. Once we obtain the very last activation map, we will flatten it into a 1D tensor and pass it through a neural network to classify the image. These are what the kernels actually look like. They don't have to be, but typically kernels are a 3x3 matrix like the one shown here. The numbers in this matrix would be set by the algorithm after the model is trained. As an example, we have on-screen an edge detection and image sharpener kernel. You can play around with it, but essentially, when you apply these kernels, they produce an output feature map. As you can see, applying the edge detection kernel will give you an edges map, while the sharpener detection kernel will give you a sharper version of the image as its map. These are simple kernels that result in simple feature maps, but we can build on top of these simple maps to create much more complex ones in order to classify things such as faces, tails, legs, and more. Here's a look at how the math works behind a kernel. Images are represented by matrices filled with pixels. The 6x6 gray box represents a grayscale image, and the 3x3 matrix represents the filter. You will move the filter across each of the pixels and do a dot product multiplication in order to get the corresponding output, which is now the resulting feature map. Though it might look complicated, all the filter does is multiply the numbers in the matrix with the corresponding pixels that the matrix is on, then summing up that total value. After this feature map is created, a ReLU activation function is applied onto each value of the matrix. The ReLU activation function is very simple, and all it does is change all the negative values to 0 and leave all the positive values as is. The main purpose of the ReLU function is to increase computational speed, and you can see how this ReLU function is applied to every pixel in the image. However, one limitation of the output feature map is that they can be really precise and pick up on all the small details, meaning that even the smallest of changes to the image, such as a minor rotation or translation, can result in a completely different feature map and thus an incorrect classification of the image. A common approach to addressing this problem is called downsampling. This is where a lower resolution of a feature map is created, one that still contains the main features, but without the fine detail that may not be as useful. By removing these details, we are able to generalize the features at a much higher level, so minor changes will not affect the classification process as much. The way this works is with a pooling function. The most common pooling function is known as max pooling, with a size of 2x2 pixels and a stride of 2. Max pooling takes the largest value within each of the 2x2 box it forms. This helps to create the lower resolution version of the image while still containing the main features needed to identify it. As you can see, the 4x4 input map is scaled down to a 2x2 one. Thus, pooling reduces the dimensions of a feature map, which will be computationally beneficial later. Let's recap everything we just went over. We begin with an input image. This is passed through a convolutional layer with a ReLU activation function applied on it, and then is sized down due to pooling. This occurs 2 times, and finally, the last resulting output map is flattened into a 1D tensor and connected to a simple neural network, which will then output the labels and classify what the inputted image is. The model will be trained with many sample data images and improved through a process known as backpropagation, which minimizes the error between the predicted image and the actual image. The model will use backpropagation to tweak the numbers in the filters until it becomes as accurate as possible. Convolutional neural networks are extremely powerful, and they are what makes facial technology possible. And it doesn't just stop there. They can be used to help advance driverless cars, analyze documents, predict weather, diagnose medical problems, and so much more. Use of CNNs is growing exponentially, and they're not stopping anytime soon. With its numerous applications and widespread benefits, convolutional neural networks will definitely be an integral part of our future. Thank you.